Variable primary flow has become the industry standard for water-cooled and many air-cooled chilled water pumping system designs because of its low installed costs, reduced mechanical room footprint, high system efficiency or low operating costs, and its better response to low delta T syndrome. Let's discuss each of these benefits, comparing a variable primary system, also known as VPF, to the second most common pumping arrangement, primary secondary, starting with low installed costs. VPF offers building owners lower installed costs versus the primary secondary arrangement because of its simplified design. Specifically, owners would see savings related to the elimination of secondary pumps, plus their associated piping, valves, control wiring, and on-site rigging and installation costs. Note that those savings are partially offset by the VPF system's additional bypass valve flow meter tandem, but the net installed system savings is still typically about 5%. The second benefit of a reduced mechanical room footprint again correlates to the simplified system design. In other words, with less system components, more building space can be dedicated to serving the building's purpose, such as additional classrooms, office space, patient rooms, etc. Thirdly, and usually most importantly, variable primary flow systems will save more pump energy than any other pumping system arrangement. And there are two main reasons why. First, with VPF, you have one set of pumps, all of which are variable speed, versus primary secondary where you have two sets of pumps, with one of those sets being constant speed, or on-off. So as building load changes, the building owner with a VPF system would be able to optimize their controls to vary pump speed and staging to most efficiently match the system load. Where with a primary secondary system, they would have to simply cycle pumps on and off to meet or exceed the load.
Second, again related to system design, the total required pumping power will be lower with a VPF arrangement. To illustrate why this is, let's reference the pump power equation, where design kilowatts equals system flow times system head over 367 times the efficiency of the pumps being used. First, for the example 1,350 cubic meter per hour chilled water system shown, we now know that the VPF arrangement eliminates the need for secondary pumps, and accordingly the system losses associated with those pumps, strainers, valves, etc., which ends up being about 3 meters of head, or in this case, 7% of the total system head. And this decrease is pretty typical, and it directly translates to operational savings.
Additionally, the VPF pumps should operate at a more efficient point on their pump curves versus pumps in the primary secondary system. Again, using this same example, let's assume we have constant speed pumps with a 74% efficiency, and let's focus on comparing the efficiency of the variable speed pumps.
Looking at the pump curve for one of the secondary pumps, we can see it would operate at an 80% efficiency based on its design conditions of 450 cubic meters per hour and 30 meters of head. Then, using this same curve, let's look at what the efficiency of a pump in the VPF system would look like. Each pump will still be operating at 450 cubic meters per hour, but remember the individual pump head is higher at 42 meters. When this is mapped, we can see the resulting pump efficiency of 86%, meaning they will better utilize the power they receive.
Completing the equation, we see that the building owner will end up saving about 15% in chilled water pumping power if a VPF system is implemented. To summarize, with all operating advantages combined, building owners should see about a 20 to 30% savings in total chilled water pump energy, or about 4 to 5% in total plant energy. In other words, a VPF system should cost less to install, save building space, and it should cost less to operate. Then lastly, a VPF system will have a better response to low delta T syndrome as compared to a primary secondary system. Low delta T is a situation when, because of one of several potential chilled water or air side issues, the system ends up pumping more water than is actually required for the building load, thus wasting energy. A common example here is when the air handling unit is not properly maintained and the cooling coils clog to some degree on the air side with dust. When this happens, the required heat exchange is not occurring between the cycling air and the chilled water system. Therefore, the system thinks more chilled water flow is needed to compensate for not meeting the building load, and the controls tell the chilled water pumps to speed up or stage on. As you can imagine, when this happens, more flow is actually being circulated than is needed, which of course leads to increased plant energy costs. The advantage with a VPF system is the pumps can be sped up to compensate as needed, as opposed to a primary secondary system with constant speed pumps, where you may need to turn on additional pumps and chillers to compensate, as primary flow always needs to be greater than or equal to secondary flow. Of course, in either case, the root cause of the issue, cleaning the dirty coils, needs to be addressed, or energy will be wasted.
York, high performance environments for life.